The idea that the universe once didn't exist is grounded in cosmological theories, particularly the Big Bang theory, which is supported by various lines of evidence. Here's how scientists deduce that the universe had a beginning. Cosmic microwave background radiation, CMB. The CMB is the faint glow left over from the early universe, about 380,000 years after the Big Bang, when atoms first formed and light could travel freely. This radiation provides a snapshot of the universe when it was extremely hot and dense. The CMB suggests that the universe had a very hot, dense and compact origin. The cosmic microwave background, CMB, is critical to scientists realizing that the universe had a beginning. Here's how the CMB directly relates to the idea of the universe having a start. Evidence for a hot, dense, early universe. The CMB is the afterglow of the Big Bang and serves as direct evidence that the universe started from a hot, dense state. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine and form neutral atoms, recombination. Before this, the universe was opaque because photons, light particles, were constantly scattered by free electrons. Once atoms formed, light could travel freely, and the radiation that was released at this time is what we observe today as the CMB. This radiation shows that the universe was once incredibly hot and dense, supporting the idea that the universe had a beginning, a point in time when it was much smaller, hotter, and more compact than it is today. Uniformity and the Big Bang model. The uniform nature of the CMB across the sky suggests that the universe was in a very homogeneous state early on. However, there are small fluctuations in temperature, anisotropies, which are crucial because they represent density variations in the early universe. These fluctuations eventually grew due to gravitational attraction and formed galaxies, stars, and larger structures. This uniformity combined with fluctuations fits with predictions made by the Big Bang theory, which says that the universe began in a hot, dense state and has been expanding ever since. The CMB provides a snapshot of the universe at a time when it was still very young, indicating that the universe had a beginning at the moment of the Big Bang. No observable evidence of the universe before the CMB. The CMB provides the oldest light we can observe, dating back to the time when the universe was about 380,000 years old. Prior to this, the universe was too hot and dense for photons to travel freely. This means there is no observable evidence of the universe existing in any recognizable form before this time. The fact that we can only observe the universe from this point forward supports the notion that the universe began at a specific moment in time, the Big Bang, and that time itself started then. Cosmological models and general relativity. The CMB also supports the predictions of general relativity, which implies that space and time themselves began at the Big Bang. According to the theory, as the universe expands, the CMB's temperature decreases, which is exactly what we observe. This further confirms that the universe started from a very hot, dense state and has been cooling and expanding ever since. By studying the CMB's temperature fluctuations and comparing them with theoretical models, scientists have been able to determine the age of the universe, about 13.8 billion years, and confirm that the universe has a finite beginning, which aligns with the Big Bang theory. CMB as a fossil of the Big Bang. The CMB is often referred to as a fossil of the Big Bang because it carries the signature of the universe's earliest moments. The fact that this radiation is still detectable today and has been stretched into the microwave region of the electromagnetic spectrum due to the expansion of the universe provides clear evidence that the universe has evolved since its inception. Expansion of the universe. In the early 20th century, Edwin Hubble observed that galaxies are moving away from us in all directions, with more distant galaxies moving faster. This phenomenon, known as Hubble's law, indicates that the universe is expanding. If we trace this expansion backward in time, it suggests that the universe was once concentrated in a very small, extremely hot and dense state. The Borde-Vilenkin theorem further asserts that any universe with an average expansion rate greater than 0 must have a beginning in time. Hubble's law, however, has several limitations in modern astronomy. Intrinsic motion. The observed velocities of galaxies can be influenced by their internal motions and gravitational interactions. complicating the interpretation of redshift data. Calibration challenges. Determining the Hubble constant relies on accurate distance measurements, which can be difficult due to the reliance on standard candles like Cepheid variables, leading to potential inaccuracies. Cosmic variability. The value of the Hubble constant has varied over time, indicating challenges in measuring cosmic distances consistently. Local versus global expansion. Hubble's law primarily applies to large-scale structures, but local gravitational effects can cause deviations from expected recession velocities. Limitations in early universe models. Hubble's law may not accurately describe conditions during the universe's early expansion, particularly when considering inflationary models. Borde-Guth-Vilenkin. The Borde-Guth-Vilenkin BGV theorem, established by Arvind Borde, Alan Guth and Alexander Vilenkin in 2003, asserts that any universe that has been expanding on average throughout its history cannot be infinite in the past, but must have a finite past boundary. This theorem is significant as it applies universally, independent of the specific physical conditions or theories governing the early universe. It demonstrates that if the universe is expanding, it must have originated from a singular point in time, implying a beginning to the universe itself. Arguments against the Borde-Guth-Vilenkin BGV theorem's claim that the universe had a beginning include interpretation of boundaries. Some critics argue that the BGV theorem indicates a boundary in spacetime, but does not necessarily imply an absolute beginning. There could be prior cosmological models beyond this boundary. Quantum gravity considerations. The theorem is based on classical spacetime and does not account for quantum mechanics, which may alter our understanding of time and space at extreme scales. Potential for eternal models. Some physicists suggest that if certain assumptions of the BGV theorem are violated, models of an eternal universe could still exist, challenging the necessity of a beginning. These points highlight ongoing debates in cosmology regarding the implications of the BGV theorem. Redshift and the Big Bang model. The redshift of light from distant galaxies shows that they are moving away from us, meaning the universe has been expanding over time. The redshift data fits with the predictions of the Big Bang theory, which suggests the universe began from a singularity, a point of infinite density. Theoretical models and general relativity. Albert Einstein's theory of general relativity provides the framework for understanding how space, time, and matter interact. When applied to the whole universe, it suggests that space and time themselves began at the moment of the Big Bang, and the universe, as we understand it, didn't exist prior to this event. Einstein's theory of relativity, particularly general relativity, supports the idea that the universe has a beginning through several key concepts. Curvature of spacetime. General relativity describes gravity as the curvature of spacetime caused by mass and energy. This framework allows for dynamic models of the universe, leading to the understanding that if spacetime is curved, it must have originated from a singular state, aligning with the Big Bang theory. Expanding universe. Einstein initially proposed a static universe, but later adapted his equations to accommodate an expanding universe after Hubble's observations. This expansion implies that the universe was once concentrated in a hot, dense state, supporting the notion of a beginning. Cosmological models. The work of physicists like Georges Lemaitre, who applied Einstein's equations to cosmology, led to models suggesting that the universe evolved from an initial singularity, reinforcing the idea of a finite past. Thus, general relativity provides a framework that fundamentally supports the concept of a universe with a beginning. Observing distant galaxies, astronomers look back in time. The farther away a galaxy is, the further back in time we are looking. The most distant galaxies observed are only a few 100 million years old, meaning they formed after the Big Bang, and earlier stages of the universe remain opaque to us due to the dense and hot state of the early universe. As galaxies move away from us, their light shifts toward longer wavelengths, indicating that they are receding. This relationship was first established by Edwin Hubble, who found that more distant galaxies exhibit greater redshifts, suggesting that the universe is expanding uniformly. The redshift can be interpreted as a result of light traveling through expanding space, reinforcing the idea that the universe has a finite age and originated from an initial singularity. Cosmic nucleosynthesis. Cosmic nucleosynthesis is the formation of new atomic nuclei from protons and neutrons in the universe, primarily occurring through processes such as Big Bang nucleosynthesis and stellar nucleosynthesis. The formation of light elements like hydrogen, helium, and lithium in the first few minutes after the Big Bang, called Big Bang nucleosynthesis, provides strong evidence that the universe began in a hot, dense state. The amounts of these elements observed today match predictions made by the Big Bang model. Big Bang nucleosynthesis, BBN, occurred within the first minutes, producing about 25% helium and trace amounts of deuterium and lithium, consistent with observed cosmic abundances. The predictions of BBN, based on the universe's initial conditions, align with measurements of cosmic microwave background radiation, further validating the hot Big Bang model entropy and the arrow of time. Entropy is often described as the arrow of time because it provides a directionality to time based on the second law of thermodynamics, which states that in an isolated system, entropy tends to increase. This means that spontaneous processes, like mixing or aging, occur in one direction, from lower to higher entropy, thus defining our experience of time moving forward. While entropy increases, our perception of time is also influenced by memory and causality. We remember the past but not the future. However, the second law of thermodynamics states that entropy, disorder, increases over time. If the universe has been expanding and increasing in entropy, it implies that it started from a very low entropy state, suggesting a beginning. The concept of time itself began with the Big Bang, quantum mechanics, and the pre-Big Bang era. Quantum cosmology is an area of theoretical physics that tries to apply quantum mechanics to the entire universe. One approach suggests that the universe could have undergone a quantum fluctuation from a state of nothing or a quantum vacuum. In this framework, the universe could have emerged from a quantum field, or a state where classical ideas of time and space don't apply. The idea of nothing in quantum mechanics is different from the philosophical or intuitive idea of emptiness. It's a kind of quantum foam filled with fluctuations and energy. Some theories, such as eternal inflation, suggest that the universe could have emerged from a larger multiverse, where different pocket universes form continually. In this view, there may be no single beginning, and our universe could just be one in an infinite series of universes. Theoretical models and multiverse theories propose that our universe is just one of many in a vast multiverse. In this scenario, each universe could have its own set of physical laws and constants. Some multiverse models suggest that universes constantly come into existence through processes like eternal inflation, which could imply that there is no singular origin or before the universe, but rather an ongoing process of creation. In this context, the question of what existed before our universe might be replaced by a larger context of an infinite or cyclical multiverse. Philosophical considerations. From a philosophical perspective, the concept of before the universe is tricky because it assumes that time itself existed in some form before the Big Bang. However, in the context of modern cosmology, time began with the Big Bang. Some philosophers argue that it may be meaningless to ask about events before time began, because our concept of time is tied to the structure of the universe. Some philosophical interpretations propose that the universe is eternal and does not have a beginning or end. These views often come from ancient traditions, but modern science tends to favor models that suggest a definite beginning point. The role of singularity in general relativity. According to Einstein's theory of general relativity, the Big Bang singularity is a point where our understanding of space and time breaks down. A singularity represents a region of infinite density, where the known laws of physics cease to function predictably. Before the Big Bang, the equations of general relativity suggest that all matter and energy were compressed into this singularity. But general relativity does not provide insight into what, if anything, existed before this state. The breakdown of physics at this point means that new physics, likely involving quantum gravity, would be needed to explain the true nature of the origin of the universe. What nothing means. In modern physics, nothing does not refer to the absolute void of space, but rather a quantum vacuum, which is still a fluctuating and active state. In this sense, Nothing could be thought of as a state where particles and energy exist in a probabilistic state but don't yet form a full-fledged universe. Some theories propose that the universe could have arisen from such a vacuum through a quantum fluctuation where energy spontaneously forms into matter and space-time as we know it. The question of whether the universe is eternal remains a topic of debate among scientists and philosophers. Some cosmological models suggest an eternal universe, indicating no singularity from the infinite past to the future, with ongoing evolution but no definitive beginning or end. However, other analyses argue that while the universe may expand indefinitely, it must have had a beginning due to mathematical constraints related to its expansion dynamics. The concept of eternal inflation proposes that our universe is just one bubble in a larger multiverse. But even this model implies limitations on the past eternity of individual universes. Arguments for and against an eternal universe are deeply rooted in both philosophical and scientific discourse. First, we will be discussing arguments for an eternal universe, and then we will go to the section where we discuss the arguments against the eternal universe. Oscillating universe theory. This theory posits that the universe undergoes infinite cycles of expansion and contraction, suggesting no definitive beginning or end. Quantum vacuum fluctuations. Some propose that the universe could arise from quantum fluctuations in a vacuum, implying a potentially eternal existence without a singular starting point. Philosophical support. Philosophers like Aristotle argued for an eternal cosmos, asserting that an infinite past avoids the contradictions of a beginning, as nothing comes from nothing. Arguments against an eternal universe. Callum cosmological argument. This argument states that everything that begins to exist has a cause, leading to the conclusion that the universe must have begun to exist, thus requiring a cause. Problems with actual infinity. Critics argue that an eternal universe implies an actual infinite number of past events, which leads to logical absurdities and contradictions in reality. Scientific evidence. The Borde-Guth-Vilenkin theorem suggests that the universe has a past boundary, supporting the idea of a finite beginning, consistent with the Big Bang theory. The evidence from various fields of astronomy, physics, and cosmology supports the idea that the universe began from a state of extreme density and temperature around 13.8 billion years ago and has been expanding ever since. This strongly suggests that, before this event, the universe did not exist in the form we know today, leading to the conclusion that it once didn't exist in its current state.